Welcome to week 2 of Fundamentals of Experimental Design. This week we're going to talk about the science process itself. In so doing, we're going to talk about some basic assumptions of science. As we learned last week, science uses observations and reasoning to build reliable knowledge about the world around us. We're going to watch a TED-Ed video similar to the TEDx videos that you may be familiar with, or the TED Talks. And this one is about how simple ideas lead to scientific discoveries, a tiny history of scientific discovery.
One of the funny things about owning a brain is that you have no control over the things that it gathers and holds on to, the facts and the stories, and as you get older, it only gets worse. Things stick around for years sometimes before you understand why you're interested in them, before you understand their import to you. Here's 3 of mine. When Richard Feynman was a young boy in Queens, he went for a walk with his dad and his wagon and a ball. And he noticed that when he pulled the wagon, the ball went to the back of the wagon. And he asked his dad, why does the ball go to the back of the wagon? And his dad said, that's inertia. He said, what's inertia? And his dad said, inertia is the name that scientists give to the phenomenon of the ball going to the back of the wagon. But in truth, nobody really knows. Feynman went on to earn degrees at MIT, Princeton. He solved the Challenger disaster. He ended up winning the Nobel Prize in physics for his Feynman diagrams describing the movement of subatomic particles. And he credits that conversation with his father as giving him a sense that the simplest questions could carry you out to the edge of human knowledge, and that's where he wanted to play. And play he did. Now, Eratosthenes was the 3rd librarian at the Great Library at Alexandria, and he made many contributions to science. But the one he is most remembered for began in a letter that he received as the librarian from the town of Swenet, which was south of Alexandria. The letter included this fact that stuck in Eratosthenes' mind, and the fact was that the writer said at noon, on the solstice, when he looked down this deep well, he could see his reflection at the bottom, and he could also see that his head was blocking the sun. Now, I should tell you, the idea that Christopher Columbus discovered that the world is spherical is total bull. It's not true at all. In fact, everyone who was educated understood that the world was spherical since Aristotle's time, and Aristotle had proved it with a simple observation. He noticed that every time you saw the Earth's shadow on the moon, it was circular. And the only shape that constantly creates a circular shadow is a sphere, QED. The Earth is round. But nobody knew how big it was until Eratosthenes got this letter with this fact. So he understood that the sun was directly above the city of Swenet, because looking down a well, it was a straight line all the way down the well, right past the guy's head, up to the sun. Eratosthenes knew another fact. He knew that a stick stuck in the ground in Alexandria at the same time and the same day at noon, the sun's zenith, on the solstice, the sun cast a shadow that showed it was 7.2 degrees off axis. Now, if you know the circumference of a circle, and you have 2 points on it, all you need to know is the distance between those 2 points, and you can extrapolate the circumference. 360 degrees divided by 7.2 equals 50. I know it's a little bit of a round number, and it makes me suspicious of this story too, but it's a good story, so we'll continue with it. He needed to know the distance between Swenet and Alexandria, which is good because Eratosthenes was good at geography. In fact, he invented the word geography. The road between Swenet and Alexandria was a road of commerce, and commerce needed to know how long it took to get there. It needed to know the exact distance, so he knew very precisely that the distance between the 2 cities was 500 miles. Multiply that times 50, you get 25,000, which is within 1% of the actual diameter of the Earth. He did this 2,200 years ago. Now, we live in an age where multi-billion-dollar pieces of machinery are looking for the Higgs boson. We're discovering particles that may travel faster than the speed of light. And all of these discoveries are made possible by technology that's been developed in the last few decades. But for most of human history, we had to discover these things using our eyes and our ears and our minds. Armand Fizeau was an experimental physicist in Paris. His specialty was actually refining and confirming other people's results. And this might sound like a bit of an also-ran, but in fact this is the soul of science, because there's no such thing as a fact that cannot be independently corroborated. And he was familiar with Galileo's experiments in trying to determine whether or not light had a speed. So Galileo had worked out this really wonderful experiment where he and his assistant had a lamp. Each one was holding a lamp, and Galileo would open his lamp and his assistant would open his lamp. And they got the timing down really good. They just knew their timing. And then they stood at 2 hilltops 2 miles distant. And they did the same thing on the assumption from Galileo that if light had a discernible speed, he'd notice a delay in the light coming back from his assistant's lamp. But light was too fast for Galileo. He was off by several orders of magnitude when he assumed that light was roughly 10 times as fast as the speed of sound. Fizeau was aware of this experiment. He lived in Paris, and he set up 2 experimental stations roughly 5.5 miles distant in Paris. And he solved this problem of Galileo's, and he did it with a really relatively trivial piece of equipment. He did it with one of these. I'm going to put away the clicker for a second because I want to engage your brains in this. Now, this is a toothed wheel. It's got a bunch of notches, and it's got a bunch of teeth. This was Fizeau's solution to sending discrete pulses of light. He put a beam behind one of these notches. If I point a beam through this notch at a mirror 5 miles away, that beam is bouncing off the mirror and coming back to me through this notch. But something interesting happens. As he spins the wheel faster, he notices that it seems like a door is starting to close on the light beam that's coming back to his eye. Why is that? It's because the pulse of light, it's not coming back through the same notch. It's actually hitting a tooth. And he spins the wheel fast enough, and he fully occludes the light. And then, based on the distance between the 2 stations and the speed of his wheel and the number of notches in the wheel, he calculates the speed of light to within 2% of its actual value. And he does this in 1849. This is what really gets me going about science. Whenever I'm having trouble understanding a concept, I go back and I research the people that discovered that concept. I look at the story of how they came to understand it. And what happens when you look at what the discoverers were thinking about when they made their discoveries is you understand that they are not so different from us. We are all bags of meat and water. We all start with the same tools. I love the idea that different branches of science are called fields of study. Most people think of science as a closed black box, and in fact, it is an open field, and we are all explorers. The people that made these discoveries just thought a little bit harder about what they were looking at, and they were a little bit more curious. And their curiosity changed the way people thought about the world, and thus it changed the world. They changed the world, and so can you. Thank you.
So science, the process, again uses observations and reasoning to build reliable knowledge about the natural world. Adam Savage in the video demonstrates how very simple ideas can turn into extraordinary understanding about things in the natural world. But it brings up, when we talk about assumptions of science, it brings up the idea or the question of whether or not there's evidence of reliability within our knowledge about the natural world. With this, I want you, with this question, the evidence of reliability, is to look around you wherever you're sitting. If you're in the library, if it's your home watching this video, look around you and take a minute to find things that might point to evidence of reliability in science, in these observations and reasonings that have led to knowledge about the natural world. And think about it for a minute. Are there everyday products of scientific knowledge? Of course there are. Things like your cell phone. You might actually be watching this video and listening to this video on your cell phone. Airplanes, antibiotics, batteries, bridges, roads. All of these technologies work because science works. We have to remember that science is a process, and it's a process of building scientific knowledge that relies on some basic assumptions. These assumptions are that natural causes explain natural phenomena, that evidence from the natural world can inform us about those causes, and that these causes are consistent. So if we look at these individually, we'll start with the fact that there are natural causes for things that happen in the world around us. An example of this is if a ball falls to the ground, science assumes that there must be a natural explanation for why the ball moves downward once it's released. Right now, we can describe gravity in great detail, but exactly what gravity is remains elusive. Still, science assumes that there's an explanation for gravity that relies on natural causes, just as there is for everything in nature. Evidence from the natural world can be described to learn about those causes. For example, science assumes that we can learn about gravity and why a ball falls by studying evidence from the natural world. To do so, scientists perform experiments with other falling objects. They observe how gravity affects the objects, and this can be applied also to observing how gravity affects the orbits of planets, satellites, etc. Observations of these effects help scientists understand more about the natural causes of gravity. There is consistency in the causes that operate in the natural world. In other words, the same causes come into play in related situations, and these causes are predictive and predictable. For example, science assumes that the gravitational forces at work on a falling ball are related to those at work on other falling objects. It is further assumed that the workings of gravity don't change from moment to moment and object to object in unpredictable ways. So, what we learn about gravity today by studying falling balls can be used to understand things like modern satellite orbits, formation of the moon in the distant past, and movements of planets and stars in the future, because the same natural cause is at work regardless of when and where things happen. These assumptions, if met, allow us to make predictions about using knowledge that is available. These assumptions are important and non-controversial in science today. However, there are still misconceptions about scientific knowledge in our communities, even misconceptions about known scientific principles like gravity. For example, when you talk about gravitational forces, a question that often arises where you can tease out that there are misconceptions about how gravitational forces work is a question about which hits the ground first. In this question, you have a 5-kilogram medicine ball versus a basketball. And the question is, if both are dropped from the same height, which one will hit the ground first?
Now I'd like you to make a prediction. In my left hand, I have a basketball. In my right hand, a 5-kilogram medicine ball. If I hold them both above my head and then let them go simultaneously, which one will hit the ground first? 6 years ago, here at the University of Sydney, I did an experiment very similar to this, where I handed out a heavy object and a light object, and I asked which one would hit the ground first. Tell me, which one's gonna hit the ground first?
I'm going to put my money on the black fella.
What's your heart telling you?
I reckon it's going to drop faster.
I'm on the black one as well. Yeah, I'll go with
Okay.
This one go faster and hit the ground first.
Pick
This one.
You gonna pick that one?
Yeah.
What's your feeling about that one? How does it compare to the...
Well, it's a lot heavier, and I just feel like the weight is, pulling it down. The more weight, the faster it's going to fall to the ground.
The forces are more on that ball than this one. You can definitely tell the difference. I mean, I go to the gym like 7 days a week, but I still feel it. I can still feel it.
Well, that one feels like it could almost go up, where this one is going down.
It's got air in it, so it's lifting up as opposed to this one being pulled down.
Now you're coming back to me, I'm thinking of basketball now.
What's making you think basketball?
Because you're coming back to him.
Sure.
I'm just saying, like...
No, I'm gonna stay solid. You can't corrupt me. I'm gonna stay solid on the black.
All right, let's actually do this thing. So do you wanna hook us up? As high as you can, and the key is to be as simultaneous as you can. All right, are you ready? You wanna count it down?
Yeah. 3, 2, 1.
Exactly the same. Oh! 3, 2, 1.
Yes! We did it!
What did you think happened?
I thought the black one went first.
You thought the black one landed first?
I agree.
We'd have to go to the tape. What did you see?
They looked like they pretty much landed at the same time.
They hit the ground at the same time.
Oh, I thought it was very close. It's probably just a bee stick in it.
It's because it's not a very high distance, so they haven't really reached their maximum velocity yet.
Well, the black ball just didn't reach terminal velocity. Wasn't enough time for it to fall.
I would thought it'd be like all the different variables, like so like that one had to like break more air, whatever.
Break more air?
You know.
The answer is, although the force of gravity on the black ball is greater, it has a greater mass and therefore greater inertia, so it requires more force to accelerate it. There's less gravitational force on the basketball, but because its mass is lower, it has less inertia and therefore requires less force to accelerate it at the same rate as the medicine ball. Let's give it a try. 3, 2, 1.
So in this particular video, most everyone says the medicine ball will drop or hit the ground first. It seems obvious that the heavy one should accelerate at a greater rate, and therefore land first because the force pulling it down is greater. This, however, forgets or ignores inertia, the tendency of mass to resist changes in motion. Therefore, although the force on the medicine ball is greater, it takes this larger force to accelerate the ball at the same rate as the basketball. Here's another video explaining the same example from a different perspective.
Let's say Jack holds both balls above his head, and then he drops them at exactly the same time. What do you expect to see?
Well, they're going to hit the ground at the same time.
I expect them to both land at the same time.
Same time.
Same time.
Well,
I think they both will.
This one to hit the ground first. However, they would actually both hit the ground at the same time.
Why is that?
Science.
Yeah, science.
Now the black one clearly feels a lot heavier. So the standard misconception is to believe that the black ball will accelerate at a greater rate and reach the ground first. This year, many people had an idea that both balls would land at the same time, but they didn't know exactly why. I found there were some different misconceptions. For example, many people seem to think that as an object falls towards the Earth, it falls with a constant speed.
From this height, yeah, pretty much.
Just a constant speed all the way down.
Speed.
Yeah, I think it'll be the same constant speed.
I think it's constant.
I seem to remember it being constant. I did decently in physics, and I seem to remember that's the answer.
Whereas the truth is, the speed of both balls is changing all the time. The balls are speeding up as they go towards the ground. That's what the force of gravity does on them. It makes them accelerate. It gets them to speed up. Another misconception I discovered was that some people believe both balls should have the same gravitational force on them, even though the black ball is clearly much, much heavier. The reason I think they said this was because they knew both balls needed to reach the ground at the same time, so they reasoned that the force on them must be the same. Tell me about how the gravitational force on this ball compares to the gravitational force on that ball.
The force is the same.
It's going to be very similar.
In terms of gravitational pull, they both have the same and they'll fall at the same rate. I don't know like Einstein, but same gravitational force around the whole world, right?
Because the gravitational pull on the Earth is the same on both objects.
Are you saying that the force on them is the same?
The pull is the same.
But you felt the pull and you've told me the pull is different.
No, I said the weight is different. I didn't say the pull is different.
It is heavier and has more gravitational pull. But when I drop them, then they get equal with gravitational pull somehow.
Don't you think it's going to be like 5 times as much?
Yeah, you think, but it's not.
The way you're asking it, yes, but scientifically speaking, no.
The gravitational force on both these balls are the same.
Okay.
The gravitational force on both of these balls is the same.
Is that what you actually believe?
No, but it is.
Tell me what you believe.
I believe it should be more on this, simply for the fact that this is heavier, and just intuition tells me that it should be more, but after learning physics, we learned that it is actually the same.
I actually think the force on this ball is more than the force on this ball.
No, you don't.
I swear. I am not trying to mess with you. So,
Like in real life?
in real life and in physics, I will tell you that the force on this ball is more. All right, ready? 3, 2, 1.
Yeah. Yep, see?
Same time.
I would say the force on the medicine ball is like a lot more because it's got a lot more weight, it's got a lot more mass, but it's got a lot more inertia.
Oh.
You guys remember that, right? It's got a lot of resistance to acceleration, so it takes more force to get it accelerating at the same rate as this ball. and that's why they accelerate at the same rate. Thank you guys so much for playing along. I appreciate that.
Sorry,
Thanks,
Derek.
Jack.
So these two videos pointed out common misconceptions, even when, in the second example, even when the people asked which would hit first, they were correct in that they hit at the same time, but they couldn't explain why. And it had a lot to do with the basic misconceptions or misunderstanding of how gravitational force and inertia work. We see these standard misconceptions across biology all of the time. It is something that we struggle with as scientists and as a overall community to deal with. And a lot of this has to do with the fact that there are limitations to science. And so it's important for us to remember that science has limitations also. Some of the basic limitations of scientific knowledge are outlined here, or listed here. The first one listed is that our senses have their own biological limitations. Even with technological devices, there are limitations to accuracy and range of our of different senses. The second one, our mental processing of sensory data is not always reliable. We are influenced by previous experiences, biases, and degrees of attention, all contingent on circumstances. This is the reason why eyewitnesses in criminal cases are not reliable. The third one, it is impossible to know if we are considering all of the possible alternative explanations. It's just impossible for us to know every possible situation. The last one, scientific knowledge, is necessarily contingent knowledge and therefore uncertain and changing. It is not absolute. It is dependent on available evidence, circumstances, tools, and our ability to analyze it. Nevertheless, scientific knowledge is the most reliable knowledge we can have about the natural world and how it works. This is because scientists have developed a methodology for learning that is based on principles of critical thinking and reducing bias. Critical thinking is something that maybe you've heard of in the last few years of your educational career. It's extremely important, and it's the way in which progress is made. And it's also the way that you can assure that you can become more successful in your own life. Critical thinking is based on tenets of how science works. The first tells us that assumptions and current knowledge, even facts, are subject to regular review and reassessment, especially in light of new evidence. Ideally, scientific observations and experimental results require independent duplication and confirmation by others to gain credibility and acceptance. Remember, in week 1, we talked about how reproducibility is one of the fundamental importances of accepting science and scientific data. When possible, additional independent data sets are sought as supportive or corroborative evidence for an explanation. We call this concordant evidence. Scientific knowledge is public knowledge, available for scrutiny and study by anyone who cares to do so. However, expertise in knowledge is highly regarded and should always remain so. But there is no reliance on or recourse to any absolute authority to determine what we consider the truth. Given this, we have to be aware of relativism. Relativism is the thesis that all points of view are equally valid. When we think of relativism, we can think of it in a lot of different ways. I have a couple listed here, a couple of examples. In ethics, this relativism amounts to saying that all moralities are equally good. In epistemology, it implies that all beliefs or religious belief systems, or belief systems in general, are equally true. Another example in politics or in political science is that all political movements are truths that are relative to the individual. Now, why is this dangerous? If we think about it from a scientific context or in a scientific context, and we go back to an example of autism and vaccines, the correlation between the two, you may be aware of that from popular press. I have just a breakdown here of why this is dangerous and how it came about, a timeline. A celebrity made a claim about correlations between autism and vaccinations. Due to this, vaccination rates of children went down significantly. And in response to this, diseases that had not been seen or diagnosed in the United States for decades are now being diagnosed and are more prevalent in children. So this is why they can become dangerous. To learn more about this, you can watch the video that's posted on Canvas called The Danger of Science Denial. It's a TED Talk, and it brings up a lot of ideas about relativism and why it's important. And we have to remember that in scientific interpretations, scientists themselves use comparative critical thinking to determine which explanation is more likely to be correct when compared to alternatives. And with the autism and vaccine question, if you will, it's not questioned by scientists who use comparative critical thinking because the scientific evidence demonstratively shows that there is no correlation between vaccinations and autism. So what is comparative critical thinking? Comparative critical thinking uses specific criteria to evaluate the merits of one explanation compared to another. Any scientific explanation must deal with empirical data, which is natural, but scientists consider one explanation better than another the more it is consistent with known natural processes, accounts for more data, especially independent data sets, when it has more reliable or greater predictive power, when it accounts for previously unexplained or puzzling phenomena, when it has fewer anomalies or expectations left unexplained, when it is simpler and less complicated, such as we call this Occam's razor, and if it provides a fertile field for future research. So these are considerations that scientists use to consider one explanation better than another. Since we only compare the explanations, like theories, we know about or have thought of at a given point in time, we can never safely conclude that we have determined the one absolute best or true explanation, because we can never be certain that someone in the future won't develop a completely new theory that is even better or more informed than our best efforts today. So it's important for us to remember that the process of science does not lead to the definitive. Even though there is uncertainty, our understanding is rooted in critical evaluation. And again, this is called comparative critical thinking. This brings us to the end of week 2 lecture. Your assignment is posted on Canvas, both parts 1 and part 2 for assignment number 1. Don't forget to complete both parts of assignment 1 in order to gain all of the credit, so 10 total points for that assignment. It is due on Sunday, January 20th by 11 p.m. Your first quiz will be January 24th. It will be posted later this week.